All right, guys, today we're going to talk about the second fundamental theorem of calculus, okay? Which, all right, the first we learned about yesterday, it basically says if you take the integral and you're evaluating at endpoints, the integral is the value of the top minus the bottom, all right? Now, we're going to this is all going to get us to like kind of discover what this is, what this derivative, the theorem of calculus is. Okay. The integral of f prime would just be f, right? So the integral of a derivative would be f evaluated from x to 10, which is f of x minus f of 10. That's the first theorem of calculus, the first fundamental theorem of calculus. Okay, does that make sense? Now this says, okay, now take the derivative of the thing that you just took the integral of, right? So this is saying, okay, now let's take the derivative of, and I just took the integral of this in the first question. So I integrated it, and I got f of x minus f of 10. Now you guys, what's the derivative of f of x? Well, the derivative of a function is f prime of x. And what's the derivative of f of 10? Well, this is a constant. And we know that the derivative of a constant is 0. So this is just giving me f prime of x. So I want you to look at something real quick. Okay? This should make some sense to you, but look from here to here. The derivative of an integral, well, derivatives and integrals are opposites of each other, so it should cancel each other out. And then we just change this t to an x, and we get rid of that because it's a constant. Because when we take the derivative of constant, it's 0. That's the second fundamental of theorem of calculus. It basically says derivatives and integrals cancel each other out. Okay? So check this out. For any constant, if I take the derivative of an integral, it just gives me that. But instead of f of t, it puts the x in there, and that goes away. Okay? So if I'm doing just an integral of f prime is f of t evaluated from x squared to 0. So it's f of x squared minus f of 0. That's what that would be. Okay? Now this is saying take the derivative of that. Now the long way that I was showing you before is now, well, what would the derivative of this be? Okay. So let's take the derivative of f of x squared minus f of 0. All right? Now, you guys, the derivative of any function is f prime, but because of the x squared on the inside, I actually have to do chain rule, right? This is a constant, and so the derivative will go away. So this actually is going to equal f prime of x squared times 2x, and the constant goes away. So let's see if we can find a shortcut way to do this, okay? Let's see if we can find a shortcut. I could say, okay, the derivative of an integral, well, those cancel each other out. Pop that right in there, so it's f prime of x squared times the derivative of the thing we plugged in. And then constants go to 0, all right? And it's this fast. You don't actually want to show work on these problems, so typically, here's exactly what I'm going to do, all right? I would go, so this one would be f prime of 2x times 2. This one would be f prime of x to the third. Oh, this is just having me do the integral. I'm sorry, you guys. Okay, so let's integrate this. That gives me f of t evaluated from 2x, x to the third. So it's f of 2x minus f of x to the third. Now, it's going to tell me to take the derivative of that, okay? So the derivative of this, what I just took over here, the derivative of this is now f prime of 2x times 2 because of chain rule, and f prime of x to the third times 3x squared because of chain rule. So it's basically, you go like this. Derivative and an integral will cancel each other out and leave that the same, and it's top minus bottom, but you just have to remember those little chain rule pieces, okay? So here's the chain rule version of the second fundamental theorem. if u and v are functions of x, blah, blah, blah. Here we go. This, the integral, the derivative of an integral is exactly that. We just plug in v, and then we do v prime, and we plug in u, and then we put u prime. And those are the chain rule parts. Okay? So, again, you're only going to use this when you see derivative integral. So when I see that, I'm going to be like, okay, derivative integral. Now, 0 is going to be a constant. So that's going to go away or go to 0. You could put a 0 there if you want. Minus, and then x will just plug in, 2x minus 3. So this is just negative 2x minus 3. The reason that it's negative is because that's on the bottom and the constant was on the top. But notice, it's like no sense in integrating it and then taking the derivative of it. You just get the same thing again. They're opposite, like, procedures, right? The derivative of an integral of that, well, look, constant. That's going to be 0. You know? I mean, I could find the integral of this and get a value of it, and then the derivative could be 0 because they're both constants. Okay? This one will go, okay, derivative integral means I just keep that the same. It's going to be x to the third squared plus 2x to the third times the chain rule of this. And then that's constant, so minus 0. Okay? So this is how the questions will appear on like an AP test. Okay, this is kind of what you'll see. So if f of x is the function that's the integral from 0 to 3x squared of 1 minus t squared to the 10th, what's f prime of x? So I'd go like this. Well, f prime of x means I'm going to take the derivative of the integral of this. Okay? And then I go, well, the derivative of an integral is, let's see. I'm going to put that in here. So it's going to be 1 minus 3x squared to the 10th times the derivative of what I plugged in, which is 6x, and the bottom is a constant, and I don't have to worry about it. Okay, so that's how it works. It's basically just like the second fundamental theorem. Derivatives and integrals are opposites of each other. Oh my goodness gracious. All right, fairly easy. So because the second fundamental theorem is so easy, we're going to talk a little bit about logs as well, right? Now guys, we know some derivatives. We know the derivative of ln of x is 1 over x, right? And we know the derivative of ln of u is 1 over u prime.
Hi everyone watching the video, it's me.
Hey, what do you guys think? Is Dallin going to watch the video today?
No.
Loser. All right. Dallin, the big loser, forgot his jacket in here, which almost ended up in the lost and found pile. All right. We remember the derivative of ln. So that tells us we have this new integral now. If you guys want to look, 1 over x is ln of x. And we've just done 1 over x is ln of x. The thing I want you to notice is its absolute value. Okay, so look, it's true that both the derivative of ln is 1 over x and the derivative of absolute value is 1 over x. Why do we have to do that? All right. Okay, so let's like take a look and see. Well, okay, so it's basically because there's like a domain restriction, you guys. Like, if I have, this is ln of x, okay? And this is 1 over x. Okay, so the problem is that, you know, my function is only defined on values bigger than 0, whereas the derivative is defined on both edges of the graph. So look at what happens when I put, instead of just ln of x, I put ln of absolute value of x. All right? Oh, why doesn't it like it? I think it wants me to put parentheses. ln of absolute value of x. Now, my domain is good because I have values on both sides and derivatives on both sides. So that's why. It has to do with the domain of ln of x not going on that side. Okay? All right, so let's do some examples here, all right? And this is nothing new. This is just going to be more practice just with like ln, okay? All right, cool. Here we go. Negative 3 over x. Now, first I want to show you something that would be kind of funny if you did this. All right. If I went and I said, oh, I'm going to bring this up, and it's going to be negative 3x to the negative 1, and I'm going to integrate it using the power rule. What would happen if I tried to integrate this using the power rule? Well, we add 1, right? So that'd be x to the 0 over 0. What? That makes no sense. And you guys, whenever you do that, and every once in a while I do that, I'm like, wait, what? X is 0 over 0? That makes no sense, okay? It's because, ooh, sorry, I got to get rid of that. All right, it's because that's not how I do the integral of 1 over x. The integral of 1 over x is ln, and if you try to do it with the power rule, you'll get something weird, right? This integral, okay, so we're actually not going to do it this way. What we're going to do is we're just going to say, oh, this is the same thing as taking a negative 3 out, 1 over x dx, so it's just ln of x plus c, okay? Would you be marked wrong for that answer right there? Probably not, but we do want to put absolute values on it when we're doing integrals. All right, so you can see me do absolute values and everything. Okay, this looks like a U substitution problem. I can't split up the fraction, you guys, because there's 2 things on the bottom, 1 on the top. If it was that, I would split it up for sure. Okay, I would split that up. But this one, it's different because it's got 2 terms on the bottom, 1 on the top. So I can't split it up. This is actually a U sub problem. Okay. U is p squared plus 1. Du, the derivative of that is 2p dp. So I need a 2 and a 1/2. Okay. So I get 1 over u du. That's cool, because this whole 2p dp turned into du, and then that turned into u. All right? And the integral of 1 over u, whenever you guys get to that point, it's just like, oh, cool, that's ln. So that's 1/2 ln u. And so at the end, I can plug it back in and say it's 1/2 ln of p squared plus 1 in absolute value signs plus c. Okay, so this is how we do ln integrals. Same idea here. If you're like, oh, what do I use for u? Okay, u, if you have a fraction, a lot of times u is going to be what's on the bottom of the fraction. Because du, the derivative of tangent, is secant squared, which was on the top of the fraction, so it's cool. This goes right into tangent is u, secant squared x dx is du, so it's just 1 over u. And the integral of 1 over u is ln u, so it's ln tangent of x plus c. Okay? Not too bad, right? All right, here's a couple more fun examples. So you guys, I can give you hints like, oh, a lot of times you're going to pick the bottom of the fraction, and that's what you. Or I could give you hints like, oh, sometimes you pick what's to a power, okay? It's not always the case. There's always exceptions, right? Like right here, if I let u be the bottom of the fraction, du is dx, and it's like, there's no, I mean, that doesn't like help me at all, right? So I'm going to try something else. This time, I'm going to let u be ln of x, because what's the derivative? Ln of x is 1 over x dx, which means this is u, and then all that is du. Now, how do I integrate u? Well, think of this as a power rule, u squared over 2. So it's the ln of x squared over 2 plus c. And it probably doesn't hurt to just go ahead and do that, but there you go. All right. Okay, for number 15, u is going to be what's inside the parentheses right here. U is 2 minus ln of x. So du, the 2 goes away. The derivative of ln is 1 over x dx. It does have a negative on there. So this is negative. And then okay. This is u to the 3rd on the bottom. All that is du. All right, you guys, now look. Is the integral of that going to be an ln? It's not. That is not going to be an ln because it's u to the 3. The only time it's an ln, if it's a u to the 1st on the bottom, it's an ln. If it's a u to the 3rd, we do that differently, right? we do u to the negative 3. And so my integral is, if I add 1, u to the negative 2 over negative 2. That can just make a half. U squared moves down to the bottom, and I could put in 2 minus ln of x. Okay, so yeah, that one we just bring the 3 up to a negative 3 and integrate that like usual. All right. Okay. Okay, last couple questions. We'll just do this real quick. Do you guys remember? Okay, so the other day we did trig integrals. Let me see if I can find them. Aha, here we go. So I wrote down all my trig derivatives. So my trig integrals are going backwards. So we only know how to do integrals of those things right there, because those are the derivatives just going backwards, okay? What you'll see is I don't have an integral of tangent, right? I don't have an integral of cotangent. Like, it's not, because those aren't derivatives of something. I don't have an integral of secant, and I don't have an integral of cosecant, okay? They're not ones that I memorized because those aren't derivatives of something, right? We don't have those. However, specifically for tangent and cotangent, there's a way to do it, to find the integral of it, and this is kind of cool. So let's start with cotangent, all right? So the first thing we're going to do is rewrite it as a fraction using a trig identity. Well, do you guys remember that cotangent is cosine over sine? And now that I have that, guess what? This is a u sub problem. If u is sine x, okay, so I pick the thing that's on the bottom. If you have a fraction, a lot of times you pick what's on the bottom. Du is cosine x dx. So I get 1 over u, and then all that is du. But what's the integral of 1 over u? Well, it's ln of u. So this is the ln of sine x. That's ln of sine. Okay? And think about it, you guys. If you try to take the derivative of that and go backwards, ln of sine would be 1 over sine times derivative of sine, which is cosine, and that's just cotangent. All right? Let's try it with tangent. I have to rewrite this as tangent is sine over cosine. I didn't put my dx. U is what's on the bottom. U is cosine. So du is negative sine, negative, negative. And I get 1 over u du. So it's the negative ln of u, so it's negative ln cosine plus c. Okay? Does that make sense? Okay, nice. One thing that I want to show you real quick, one thing I'm going to show you guys really fast. This is funny. I saw this on the AP test once. Check this out. Okay? There's another way that you can write that. If there's a negative in front, do you guys remember with ln rules how you're allowed to bring a constant in front and put it up as an exponent? You guys remember that? So this is really the ln of the reciprocal of cosine. And you know what the reciprocal of cosine is? Secant. So this and this are actually equivalent. And on an AP test one time, instead of this answer, I saw that answer. And I was like, woo, that's mean. But it's the same thing. We'll talk about that a little bit more in class, okay? So my last question, you guys, you know what? I would actually do this as u sub. Let's do it real quick. First, I'm going to rewrite this as sine over cosine. You guys, I'm not memorizing these. It's like too hard to memorize, in my opinion. It's too hard to memorize. So I let the bottom be cosine 2x. So du, the derivative of cosine, is negative sine 2x times 2. The dx goes here. Sorry about that. Which means I need to put a negative 2 and a negative 1/2. And then I have 1 over u du. Okay? So I get negative 1/2 ln of u, so I get negative 1/2 ln of my original u, which was cosine 2x, plus c. And we're done, okay? Yesterday was 10 minutes longer. Today is 10 minutes shorter. It all balances out in the end, okay, guys? Cool. If you watch this and take notes, we will do some problems in class.